Okay. All right, I think everything is good to go here. So hello, good morning. Hope you guys are having a good day today. So just a couple quick reminders. So first, our chapter 3 quiz is going to be next week on Monday. So similar to the last quizzes, it will open right at 12:01 a.m. and it'll be open till 11:59 p.m. So you will have to find a 1-hour block on Monday to take your chapter 3 quiz. There is some review material up on Moodle, and William will be having a review on Thursday of this week. So we have all our derivative stuff to go over that review. So if you're interested in that, definitely stop by. So today we are going to be working on something called the product rule. On Thursday, we'll cover something called the quotient rule, and that'll be the rest of our derivative techniques. Other than that, we're just sort of plugging along, doing our regular thing. So let's go ahead and get started. Let me switch over to the doc cam here. Okay. So last week we were focusing on something called the chain rule. And the chain rule that we were doing last week was how we dealt with what are called composite functions. So one function plugged into another function. Today we're going to learn about the product rule. So I want to take a minute to talk about what that means. So the word product means that you are multiplying two things together. So like the product of 3 and 4 is 12, right? You're multiplying two things together. So we're going to be using this rule when we have two functions that are multiplied together. And one of the key sort of skills that we're going to need to have here is recognizing that we are using the product rule, right? So we need to be able to look at a function and say, do I need to use a chain rule or a product rule? And we'll talk a little bit about how we might approach that. So the product rule, just like all our other rules, come from recognizing patterns and formulas and things like that. So this particular rule does come from the definition of derivative by using limits. I am not going to do the limits out. I don't think that that's going to be particularly helpful in this case, but do know that if you were to use the definition of derivative to do the limits, we would get the product rule. And so the product rule that we're going to be using looks like this. So if you have f times g and you want to take the derivative, so one function times another one, what we're going to get for our rule is that the derivative will be the derivative of the first function times the second plus the derivative of the second function times the first. So what does that mean sort of in general? It means we need to identify that we have two functions multiplied together. We're going to call one of them f and one of them g. We're going to find each of their respective derivatives, and then we're going to plug it back together in this formula, okay? So let's do an example together so we can see what this looks like and how we might put this into practice. So we're going to look at this example here. Find the derivative of x squared times e to the x. So the first thing I notice is that I have two functions multiplied together. An easy way to check if that's true is if you can draw a line that directly separates the two functions, then we're talking about a product rule. You can't do that with a chain rule. Like if you try to draw a vertical line, you won't be able to cleanly separate two things. So that's one way you might want to think about it. Now, with the product rule, you pick one function to be your f and one to be your g to start working through the steps here. It doesn't actually matter which one you pick to be f and which one you pick to be g, because all the operations we're going to do are commutative. But the convention is that the first function you see is your f and the second function you see is your g. So in this case, my f of x, I'm going to pick x squared, and my g of x, I'm going to pick to be e to the x. Now, one of the things that you're going to notice that I tend to do, and I think this is a really good habit to get into, is I write my f function, and then to the right of it, I write my g function. I'm going to need to take derivatives of both pieces, and I always write my derivative underneath the original function. And the reason I do that is because later in this class, and if you go on to 128, you're going to learn how to undo derivatives. And so when I do that, I write my derivative underneath and then go up. So it helps me have a visual of which direction I'm going. And so I always write my derivatives underneath the original. You don't have to do that, but I think it can be helpful for some of the later techniques you might learn. So by splitting up functions by f and g, the hope is that we can now take the derivative of each of these pieces. So here, my x squared, I know I'm going to have to do a power rule because my x is in the base and I have a number in the power. So the derivative of x squared is 2x. Over here, I have e to the x. I want to take the derivative of e to the x. That's an exponential with a special rule. The derivative of e to the x is e to the x. Okay. So now that I have all my pieces, my formula says that I'm going to multiply f prime times g, and then I'm going to add to that g prime times f. Okay, so when I do f prime times g, I get 2x e to the x. And then I need to add to that g prime times f. So I have x squared e to the x. Now I want to talk about how we write these terms just so that we're on the same page, that they mean the same thing. Typically, terms that are all multiplied together are listed in order of difficulty. So polynomials will typically come before exponentials. So x squared times e to the x is the same thing as e to the x times x squared, but we'll typically write the x squared first. Okay. The other thing is we could factor this in a couple of different ways. So I just want to show you just to make sure we're all on the same page about what things could look like. This is the most common answer. If this is Wiley, you can enter it like this. But we could factor out the e to the x. So that shows up in both terms. And that would leave us with 2x plus x squared. That's one way we could factor it. We could also factor out an e to the x and an x term. If we also had an x factored out, we would have x e to the x times 2 plus x. So these all mean the same thing. These are all the same mathematically. This is the most common way you're going to see it, but just know that if you're going to factor, that's what it would look like. Okay. So I'm going to have you try the next one, example 2. So here we have the natural log of x times e to the 6x. So we have to remember what happens with this 6 here, but we want to apply the product rule. So again, I know that I can apply the product rule. I can very easily separate these two functions with a vertical line. So that tells me that's the right rule to use. So I'd like you to take about 2 minutes and go ahead and set this up. We're going to call the ln of x f of x, and then g of x will be e to the 6x. Find each of their respective derivatives, and then we're going to plug it back into that formula. Okay, so take 2 minutes, try it out, and then we'll go over it together. All right, take about 30 more seconds. All right, so again, I see that I have two functions multiplied together. I'm going to call the first one f. I'm going to call the second one g to use in my formula. Now I'm going to take the derivative of each piece. Hopefully these pieces are back to the basic building blocks. Again, basic is not easy, but it's just our list of all the derivative types we know. The derivative of the natural log of x is 1 over x. The derivative of e to the 6x is 6e to the 6x. So remember, the 6 comes out when there's a constant up in the power. Now I need to multiply f prime times g and g prime times f to get the derivative that I want. So here, f prime times g, I have 1 over x e to the 6x. So that's multiplying this and this, plus g prime times f. So again, I'm going to write this in the order that you would probably see it written on a mini quiz or something like that. So here I had the natural log of x times 6e to the 6x. So the 6 would definitely come to the front. We always write our constants in the beginning. And then the natural log of x and e to the 6x are equally difficult. So either one of those could come next, but the 6 would definitely be pulled to the front. So our derivative is going to look like this. Okay. So we're going to try some other types of problems that use the product rule and tie it into applications that we've seen along the way. So we're just going to be practicing this rule and trying to make sure we recognize when we need to use it. Okay. So here we are going to do, let me get my index card here. We're going to try two problems. The first one is find the equation of the tangent line, which is a common problem that we've done before. We know that to find the equation of a tangent line, we need a point, we need a slope, we need to put it together in y equals mx plus b. So now the only difference is that our function happens to be cosine x times e to the x, but we know how to deal with that because we've now learned the product rule. And then the second problem is to find the first and second derivative of ln x times x to the fifth. So the first derivative will follow what we did before, and then we'll have to look at what types of functions we have with that to figure out how to get to the second derivative by applying similar techniques. Okay, so I'm going to give you about 4 minutes to try out these two problems where we're going to apply the product rule, and hopefully you can figure out how to apply it to these two problems. Again, you don't have to do them in this order. You can do either one first or second. And if you don't finish, that's totally fine. But see what you can figure out, and then we'll go through it together. So take about 4 minutes, and then we'll go through it. All right, take about 30 more seconds to finish up whichever part you're working on. All right, so let's go through these. Totally fine if you didn't have enough time to finish. So for the first one, we're back to our example of find the equation of the tangent line, right? So in order to find the equation of a tangent line, we need a point and we need a slope. So let's go ahead and find our point here. Again, it doesn't matter which one you find first. We have to put them all together at the end. So here we're going to do cosine 0 times e to the 0. So cosine of 0 is 1. So cosine starts up at 1. And e to the 0 is also 1. So 1 times 1 is going to give us a 1, which means our point here is 0, 1. So now we need to find our derivative. So in order to find our derivative, we're going to have to do a product rule. So what I'm going to do is I'm going to leave a space for our final derivative, and then I'm going to do our product rule sort of over here on the side. So we're going to pick one function to be f, one to be g. So I'm going to pick my first function, which is cosine x, to be f, and then my g is e to the x. Now I want to find each of their respective derivatives. So again, the derivative of cosine is negative sine. The derivative of e to the x is e to the x. Okay. So now when I put this together using the product rule, I'm going to do f prime times g. So negative sine x times e to the x plus g prime times f, so plus cos x times e to the x. Okay, so my first derivative looks like this. And again, I'm interested in what's happening when x equals 0. So I have negative sine of 0 times e to the 0 plus cosine of 0 e to the 0. Well, sine of 0 is 0. So this part of the term goes away. And then cosine of 0, we said was 1 times 1 is going to give me a value of 1. So again, that's the slope of my line. So now I have y equals 1x plus b, right? Because my slope is 1. You don't actually have to write the 1. You can just write it as x. I'm just writing the 1 so we remember that that was the slope. Now we're going to plug in our point. When x is 0, y is 1. So we have 1 equals 1 times 0 plus b. 1 times 0 is 0. So that tells me that b equals 1. So my final equation is y equals x plus 1. Okay, so again, process is the same for equation of the tangent line. What's changing is the type of function we're working with. For number 4, we're looking to find the first and second derivative for ln x, x to the 5th. So here I can see already that it's going to be a product rule because I can draw a line right in between my two functions. I have two functions multiplied together. Now, I'm going to draw a little block up here to use a little more space because I clearly didn't leave myself enough space here. So what I need to do is pick one of them to be my f and one of them to be my g. So f is ln x and g is x to the 5th. I'm going to find the derivative of each piece. So f prime of x is 1 over x, and g prime of x is 5x to the 4th. Okay, so again, I identified the two functions that are multiplied together, and then I found the derivative of each piece. And now I'm going to multiply these together to get my first derivative. So f prime times g. I'm going to set it up to multiply just as the rule is, and then I'll simplify. So f prime times g is 1 over x times x to the fifth plus g prime times f. So 5x to the fourth times ln x. Okay. So if I was just doing a first derivative, I would probably leave it like this or possibly simplify the first term. I am going to simplify the first term here because I have to take the second derivative. It'll make taking the derivative of that piece easier. So x to the fifth divided by x can be simplified into x to the fourth because one of the x's from here is going to cancel with the x down here. So then plus 5x to the fourth times ln x. So that's a simplification of my first derivative. So now, if I want to get my second derivative, I can go term by term. And I'm going to underline this in 2 different colors so we can kind of see the 2 terms we're working with. So the first term is x to the fourth. We can take the derivative of x to the fourth just using our power rule. And that's going to give me 4x cubed. But then here, my second term is 5x to the fourth times ln x. So in order to get the derivative here, I have to do another product rule, right? Because I have 2 things multiplied together. So again, I'm going to do that on the side. So I'll do that right over here. So my first function is my f, so 5x to the fourth. My second function is g, which is ln x. I take each of their respective derivatives. So here the 4 comes down to multiply the 5, and I get 20x cubed. And the derivative of ln x is 1 over x. So now, what am I doing with this? Well, I'm adding it. So this was the derivative of this piece. Plus, now I'm going to fill in my result from this product rule. So f prime times g is going to give me 20x cubed times ln x plus g prime times f. So 1 over x times 5x to the fourth. So again, I'm going to write it just like I would normally fill in a product rule. I use parentheses here just to highlight that this is the derivative of this whole second term. But now I'm going to do some simplification. So first I'm going to start with simplifying this last term over here. So 20x cubed times ln x plus, now 5x to the fourth times 1 over x. The x's will simplify here. And I have 5x cubed, right? So one of these x's is going to cancel here. So now I have 2 terms that have an x cubed in it. I can combine those. So I have 9x cubed plus 20x cubed times ln x. Okay, so here I have my second derivative. And again, I had to do another product rule on my first derivative to get to my second derivative. Okay, so sometimes you have to do it more than once. Very easily, I could have had to do it twice if this term didn't simplify. So you just have to carefully go through the steps to get the first derivative, simplify if you can, and then again, look at the steps you would need to go from the first derivative to the second derivative. Okay. So now the next example we're going to look at comes from physics. It's a word problem. So hopefully we can work through this. So here, the wave function for our harmonic oscillator, which is like a vibrating bond, can be written as, this is called psi, this is a Greek letter, equals a e to the negative x squared. So that's kind of small. So let me write that a little bit bigger. So we have psi equals a e to the negative x squared. Okay, so that's the function we're working with. where x is the distance from the equilibrium position. So something is vibrating, there's got to be a starting position. That's the equilibrium position. And a is a constant. So a just has to do with how quickly it's moving. Part of the process of working out the kinetic energy of the moving atom deals with the derivatives of this function. So this is a pretty typical function in a lot of things to look at how small perturbations impact bigger systems. So we don't need to know a whole lot about the harmonic oscillator in order to talk about the math behind looking at these derivatives. So there's 3 questions here. Part A is to look at this function and identify what is the independent and dependent variable for this equation. So that goes back to chapter 1. Part B is to find the first derivative of this function. So in order to do that, we have to know what is a constant and what is a variable. And for part B, to find the first derivative, we actually have to use a chain rule. So we have to go back to what we learned last week. And then part C is to find the second derivative of this function. Well, in order to go from the first derivative to the second derivative, you could probably guess we're going to end up needing a product rule. Okay, so we want to just work through these different pieces. Again, even if we don't know what a harmonic oscillator is, we should be able to look at a function and answer these types of questions just based on the structure and what's given in terms of the setup. Okay, so I want you to take about 3 minutes and see if you can answer these questions. And again, for part B, you're going to be using a chain rule. So if you need to look back in your notes, that's totally fine. And for part C, you will have to use a product rule and a chain rule. So try it out, see what happens. I'll give you 3 minutes and then we'll go through it together. All right, take about 30 more seconds. All right. So first, we're just making sure we recognize from all these letters, what is our dependent and what is our independent variable? Our dependent variable here is our psi, it's PSI. It's this Greek letter on the left. Typically, our dependent variable is whatever is represented on the left-hand side of the equation. For our independent variable, that's the one where we get to pick values to choose to put in. And so here, that's our x. So our x here is the independent variable. Okay, so hopefully you sorted that out. So now we want to find the first and second derivatives of this function, right, for parts B and C. So we start with the first derivative. And so when we want to take the derivative, we're looking at what's on the right-hand side. So I want to remind you that A is a constant. So when we find the first derivative of this function, we're looking for psi prime. We start with the constant multiple rule. So since the constant was multiplied by the function, that constant is also going to multiply the derivative. So what I notice is that my function is of the e form, which is an exponential form. So remember, with exponentials, we could reason through, or we can do a z substitution. I don't have a lot of space, so we're going to just sort of talk it through. But if we were to do a z substitution, your z would be negative x squared. Okay, but here we know that for exponentials, we get the same thing back, so e to the negative x squared, but then we have to multiply that by the derivative of the power. So when I do the derivative of the power, I just look at this negative x squared and I say, what's the derivative of negative x squared? Well, the derivative of negative x squared is negative 2x. So I have a times e to the negative x squared times negative 2x. If we were only looking for the first derivative, and this was on a mini quiz or something like that, the way that we would probably write this is negative 2a. So we bring the constants and the negative to the front, and then x e to the negative x squared. Okay, that's probably how you would see it written. And again, if yours looks like this, you can just match term by term. So there's an a, there's an a. E to the negative x squared, e to the negative x squared. Negative 2, x, x. All the pieces are there. Okay. For part C, we want to find the second derivative of this function. And so what I want to point out here is that if you look at our independent variable of x, there's an x here, and there's an x here. So it shows up twice, okay? And the other thing is that I can separate these two functions by drawing a line straight down. So that means I'm going to do a product rule because I have one function over here that has an x and another function over here that has the x. So now I'm going to have to do a product rule to get the second derivative of this function. So again, I'm going to kind of do that on the side. So my f is going to be negative 2ax, and my g is going to be e to the negative x squared. You don't have to pick your things this way. If you were working off this function, you can divide like this. So maybe your f was a e to the negative x squared and your g was negative 2x. You'll end up with the same answer at the end, okay? So as long as both of your f and your g have a function with an x in it, then you're good to go. So the 2 and the a, they can be on either side since they're constants, okay? So f prime and g prime. So here I have negative 2a times x. If you have a constant times x, that's a linear term since x is raised to the 1 power. So the derivative is just that constant. So the derivative here is just negative 2a. Over here, we have e to the negative x squared. So that's similar. That's the derivative we were sort of working on over here before. So again, we get the same thing back, e to the negative x squared times the derivative of the power, which is the negative 2x. So that means when we put everything back together, we have psi double prime. We're going to do f prime times g. So negative 2a times e to the negative x squared plus g prime times f. So e to the negative x squared times negative 2x times negative 2ax. Okay, so I'm going to do a couple of simplifications and rewrite so you can see how we would be writing this and how we might simplify it. So the first term is already in the form that we would likely to write it, with the negative 2a in front. Now, here I have a negative 2 and another negative 2. So the negatives are going to cancel, but my constant is going to become 4. So I'm going to have plus, now I'm going to pull my constant to the front, and a is also a constant, so I'm going to pull that to the front. Then I have x times x. So that's going to give me an x squared. And then I still have my e to the negative x squared term. So this is how you would likely see the second derivative simplified, by simplifying these two things that are being multiplied together. Okay, so we have a first derivative, we have a second derivative, and now we can talk about the rates of change of a harmonic oscillator if we wanted to. So again, I just want to make sure you know that even if you don't know the context of a particular word problem, we can still apply the things we know to talk about it mathematically. So even if you've never heard of a harmonic oscillator, we can still talk about the first and second derivatives of the function. We just have to be clear about what the function is and then apply the techniques that we know. So one of the things I want to point out that happened here that's really interesting is that we started with a chain rule. Right? So the chain rule turned into a product rule because when we did a chain rule, we ended up with a product of two functions that have the variable. So it's not uncommon for the chain rule to be paired with the product rule. So the next problem we're going to do is it's going to go ahead and think about, well, what if the terms in our product rule are composite functions, right? Can we combine what we know about the chain rule and the product rule to figure out the first derivative of a function? So this one is a little more complicated algebraically, but as long as we're really careful with our pieces, then we can get to the first derivative. So I'm going to have you try this. And here is sort of my bigger advice is that the first and outermost thing that we want to do here is a product rule, right? I can draw that line. I have two separate functions. So I'm going to call one of them f and one of them g, and then find each of their derivatives. And it's within that step of where I'm finding the derivatives that the chain rule comes in. So as long as I write things out carefully and organized, then you can put everything back together in the product rule. Okay, so I'm going to give you about 3 minutes. Try this one out. Try to be careful with the algebra. If you get it all finished and you feel like there's something you think should be simplified, you can go ahead and do that. If you don't see anything that should be simplified, don't worry about it. I don't remember if there's any simplification here, but try it out, see what you can come up with, and then we'll go through it together. All right, take about 30 more seconds. All right, so one thing I want to talk about before we even do the derivatives. So here we have sine of x cubed. Sometimes this is written as sine cubed of x. Those mean the same thing. Okay, so if the 3 is next to the sign or if it's after the parenthesis, these two things mean the same thing algebraically. I know for some reason sometimes students don't know what this means when the 3 ends up next to the sine or cosine. So I just want to point that out. So if you ever see sine cubed of x, that's the same thing as sine x all cubed. Okay. Okay. That being said, we want to separate our two functions. So you have sine of x cubed and the natural log of x squared minus x plus 1. So the first one I'm calling f and the second one I'm calling g. Now, in order to get f prime, I need to do a chain rule here. And I see that I have a variable in the base and it's raised to the power. So I'm using the power rule form. And so the power rule, the 3 will come down, everything inside will stay the same, and I subtract 1 from the power. So I have 3 times sine of x squared, but I have to remember to multiply that by the derivative of the inside. So the inside here is that sine of x function. The derivative of sine is cosine. So that is using the chain rule, the power function form. Over here, I have a natural log form. And so the derivative is 1 over whatever is inside. So x squared minus x plus 1. But I have to multiply that by the derivative of the inside, which is going to get multiplied by the 1 in the numerator. So the derivative of x squared is 2x. Now I have minus x, the derivative of minus x is minus 1. So remember there's an invisible little 1 there. And the derivative of 1 is 0. So now I have all the pieces to put together to get my final derivative here. Let's see, we're going to do f prime times g. We're going to get a lot of space here. There's a lot of terms. So f prime times g. So I have 3 sine x squared times cosine x times g, which is ln of x squared minus x plus 1, plus, now I'm going to do g prime times f. Okay, so remember, when you multiply a function into a function that looks like a fraction, a rational function, this term gets multiplied into the numerator of the function. So I'm going to write this as sine of x cubed, right? That's my f, times 2x minus 1, that's what's in the numerator here, divided by x squared minus x plus 1. okay? You don't have to write that into the numerator. You can write it like right to the left of it times and then that function. Either one is fine. It's just a matter of preference. So you can see that the derivative looks pretty long and complicated. However, if you notice that we just broke things down into smaller pieces and steps, then we're able to get all those pieces that we needed to put together to get this derivative. Okay, so again, being organized and being careful in writing down your steps helps us to stay organized to get this particular derivative. But as you can imagine, if you have chain rules within product rules, it does take a little more attention to all the details to be careful. Okay, so let's take a look at the next problem. Whoop. That's goofy. My line didn't print. Okay, e to the x over x to the fifth. So we want to find the derivative of the function e to the x over x to the fifth using the product rule. So what I want you to notice here is that right now, this is not written as a product, right? I don't have something times something. I have something over something. So what we need to do is we need to figure out how can we rewrite this function to be something times something else. And so I want to remind you that we can bring a term up from the denominator by changing the power to be negative. Okay, so here I need to rewrite this function as e to the x times x to the negative fifth. So again, I can bring this up by changing the power to be negative. Okay, so I want you to take 2 minutes, okay? Do the product rule here. We have two functions multiplied together. I can tell that it's a product rule because again, I can just separate them, right? By drawing a line right in between them, pick one to be F, one to be G, do all the parts, multiply together, take about 2 minutes, and then we'll go through it. All right, take about 30 more seconds. All right. So again, first we rewrote this by bringing this term up. So we have e to the x times x to the negative 5. We call the first function f and the second function g. Now we're going to find each of their respective derivatives. So the derivative of e to the x e to the x, same thing back. The derivative of x to the negative 5 is negative 5x to the negative 6. So remember, things get more negative when you have a negative power. So now we want to multiply f prime g plus g prime f. So our derivative here, f prime times g, we have e to the x times x to the negative 5 plus g prime times f. So negative 5 x to the negative 6 times e to the x. How might we rewrite this, right? So we could put this back down below. So e to the x over x to the 5th, right? So we can bring it back down by putting the power back to positive. Now here I have plus a negative, so I can make that minus. And similarly, so the 5 and the e to the x, those can stay in the numerator because those don't have negative powers. However, this x to the 6th term can go back down by using that same algebraic method where we can move things down if we change the sign of the power. So this is another way that we could write that answer. You could certainly factor things out here as you went, but it's unlikely that we'd be factoring at this point. We will be factoring quite a bit in chapter 4, but these are sort of the two common ways that you might see this written. Okay, so this particular example, we're actually going to do again in the next class, because next class we're going to be talking about the quotient rule, which is one function over another one. But what I want to highlight here is if you have one function over another one, sometimes you can turn it into a product rule to make the derivatives a little bit easier. Okay, so we're going to stop here. That's the last example of the product rule. So you have a little extra time today. I strongly recommend that you work on the homework and do the product rule problems and try those out before we get to Thursday's class when we're doing the quotient rule. That'll give you a good jump start, and that'll help you prepare for Wednesday's quiz. Okay, have a great rest of your day, and I'll see you all on Thursday.